All right, we're looking today, starting out looking at logarithms, and so our laws of logarithms. And so when we talk about logarithms, these are kind of key to whether it's just understanding the decibels and the intensity of sound, or a pH scale, dosing of medicines, the growth of memory and exponential function on my computer, or even looking at your financial growth or population growth. They can all be represented using some easier numbers through these logarithms. So, looking at our three rules here, and you're going to notice these are very similar to our power rules. That if I was doing uh, 5 to the third power times 5 to the second power, then it's going to equal 5 to the 3 plus 2 power, or 5 to the fifth power. So this is similar in the fact of it. If I'm solving for the log of something, so log 5 of 125 equals to x, that just says, okay, what power would I raise 5 to get to 125? So you can also look at it as 5 to the x power equals 125, and we just say x equals 3. So the the number we kind of look for and get as our answer is that power, and so that's why we can use it for so many different things. Is because when we get that value of 3 versus going up and doing 5 to the 10th power, you get a really big number. It's a lot easier to say, well, the log of that is this, and so if we know it's a logarithmic function, we can just represent it using a much smaller number. So our first law here is that log of b of m times n is log b of m plus log b of n. Similar to that, if we're multiplying two of the same number to a certain power, we would add those numbers together. And same if they're dividing, then we would subtract those numbers. So log b of m over n would be the same as log b of m minus log b of n. And just like our power rules, if we had 5 to the third power to the second power, then what I'm really doing is multiplying 5 to the 3 times 2 power to get 6. That if I have log of b m to the k power, we can move that to the front and multiply it by our answer, because any powers, since this is essentially getting what the exponent is for b anyways, if I'm raising that answer to another exponent, then we just multiply those together to get our answer. So we're going to use these three laws to split these apart. And on my first one, it's log 2 of 5 times a times b. So everything's being multiplied together, all the same log value. So, and I got to remember to write these logs in cursive, that way they separate a little better. So log 2 of 5 plus log 2 of a plus log 2 of b. So that would be mine. We're expanding them. So I could find what the exponent of that, what exponent would I put with 2 to get to 5. And in a lot of these instances, you'll get a decimal number of some sort. But a lot of applications with this when we plug in different things for A and B, or for the answer and things like that. Okay, on number 2, log 5 of 8 over x. That's our second law up there. So we're just subtracting. It would be log 5 of 8 minus log 5 of x. Okay, on number 3, 3 and 4, I'll split up into a couple of steps. But essentially, for this one, we are using the first rule and then the third rule. So you can kind of do it all at once, which would be breaking it apart into 3 pieces and moving the 2 and 3 up front. But I'll show it to you in 2 steps. So first, we'll split them all up. So log 2 of 6 plus log 2 of x squared plus log 2 of y to the third power. And then my log 2 of 6 will stay the same. And then log 2 of x squared, remember that 2 is going to move up front. So I have 2 times the log of 2x. And again, the reason that works is just like our power rule, because log 2 of x essentially gives you what exponent of 2 would equal to x. And so whatever exponent of 2 that would equal to x squared is the same thing as multiplying that answer times 2, just like our power rules multiply. Might sound a little confusing right now, but as you work with it and we kind of solve the equation part, hopefully that starts to kind of mesh together and you look back on it and say, oh, okay, that's what he meant when he was saying all that stuff. So 3 times the log 2 of y. And so that would be our expanded form of that one. Now on number 4, log 3 of a squared over bc squared, or 4a squared, there on top. I'm going to split this apart into 2 separate sections. So just know that anything that's in the denominator here, we're going to subtract. Anything in the numerator is going to add. So you can kind of think of it as the first split being log 3 of 4a squared minus log 3 of bc squared. And so this minus sign is going to go with anything that gets split apart here from here on out. And so when I split these apart, I'm going to go ahead and move that 2 up front for the part that has the a. So we start out with log 3 of 4 plus 2 times log 3 of a. And now remember, everything here is going to be minus. So minus log 3 of b, and again minus 2 log 3 of c. Okay, and you could put these 2 in parentheses and have it as a plus sign there and a minus sign there. It would work the same way, but this way gets them to be fully independent of one another, so that you could just work on one section and not have to consider the others if you needed to. Okay, then we have this on number 5, the log of the square root of a to the 5th over b. So to change that right off the bat, so remember that the square root is really just going to be the same thing as having something to the 1/2 power. And so it's log of a to the 5th over b to the 1/2 power. Well, that means that 1/2 can go ahead and move up front to get 1/2 log a 5 over b. And going from there, when we split this up, this whole, so because I'm halving this, that 1/2 is going to have to stay with both parts. So I have 1/2 And we'll just do it in parentheses because that a to the fifth. Go ahead and move the 5 up front. 1/2 times 5 log of a minus log b. And anytime you don't have a subscript number down there, we consider that to be 10. And so anytime you're working with logarithmic functions, you normally are going to adjust them to where you get to the power of, like, you get a 10 down there so that you're looking at something to the power of 10. And again, we want this to be totally independent of one another. So I need to multiply both by 1/2. So this 1/2 I'm going to distribute into both of these, which is going to give me 5/2 the log of a minus 1/2 log b. Now we've got them totally independent of one another, so we are good to move on with that one. Okay, looking at the back. We're using now the laws to condense them, and it puts that note there. It really should have been on the end of the front page. But yeah, when no base is written, then it's a base of 10. So the reason that's so important and used so often is because when you do 10 to the whatever power, that's our place value system. And so your logarithmic functions normally work off of a place value type system. Okay, looking at this first one, we have log 5 of 7 plus 3 times log 5 of x. Well, now we're going to kind of reverse the process and say that 3 is going to go up there as an exponent, and these are going to be multiplied together. So it'd be log 5 of 7 times x to the third power. So condensing it to where we've got just one log. There's our goal now for this. So you'll need to be able to work these back and forth both ways in order to work with them when we get into equations and things like that. Next, I have log 2 of x minus log 2 of 3. So that we're going to write as log 2 of x over 3. And again, just one step there. Okay, now with our 1/2, we'll keep it as a 1/2 power. If you need to, just for clarity, you can write it as square root, but it works either way. So we'll split this up into 2. We've got log 6 of m to the 1/2 power minus log 6 of n to the third power. And so that'll just be written as a fraction because those, when I put it together, those will divide. So log 6 of m to the 1/2 power over n to the third power. A couple more here. So we're going to combine inside the parentheses first. Then we'll put that to the third power. So that gives me log 2 of a minus log 2 of b would be log 2 of a over b. And then instead of putting 3 up front there, we can say, well, I know that's really going to turn into an exponent. So we can do our parentheses and put all those to the third power. And yes, you could put log 2 of a to the third, b to the third. But having it like this, it's a little more condensed, a little better combined because you can work within the parentheses, then do the third power there. Just works out a little bit easier if you're solving. Okay, on number 10, log 3 to the 4, 3 log m minus 2 log 3 of n. See if we can kind of do that just in, this is going to move up there. And You're thinking, well, could the negative move with that 2 to be log 3 of n to the negative 2 power? Absolutely, it could, but it still means the same thing. So if we do n to the negative 2 power, then it's going to be going into our power rules again of anytime it's a negative, that moves it down on the other side. So it goes from being in the numerator to the denominator. So you could say, if I did that, well, and really let's just stick with what we know. So log 3 of 4 plus 3 log 3 of m going to give us log 3 of 4m to the third power over n to the second power. That would be our whole answer. So it could be written as log 3 4m to the third power n to the negative 2 power, which technically does work. Just formatting wise, it's a little better, a little more easily recognizable when you have it that way. So really we'll stick with that one there. Okay, then we've got our change of base formula. So to do that, we need to use calculator because we're not going to really want to work these out by hand. And so then we have, in this change of base formula, the great thing about this is that once we condense this, so if I've got it log 2 of 25, if I take if I change it to a different base, and so just about every time, really what we're going to do is b is going to end up equaling 10. But what they told us up here is that when there's no base, it's understood to be a base of 10, which is a common logarithm. In other words, it's the logarithm that has a button on the calculator right at the front. So if I do log 2 of 25, that means I'll do just log 25 over log 2. And we're going to do an estimate, so we do our squiggly equal sign. And if I type that in, I've got log 25 over log 2, and that'd give me 4.644. So again, a little bit of an estimate, but working with those power rules, normally this is the output of, if you're looking at difference in sound decibels or pH scale, you would use that right there. So same thing here. I've got log 5 of 12. It's going to be log of 12 over log of 5. So put that in my fraction, and we're doing log button right here. So doing the log of 12 over, I'm going to have to delete that, over the log of 5, and I get 1.544. Okay, and even if we've got like 13 where it's a decimal, we'd still do the log of 5 over log of 0.5. And if we put that in the calculator, this is where we're going to get log of 5 over log of 0.5. So we get a negative number, just meaning that our answer would be a fraction, or so it'd be something to the negative 2.322 power. So negative 2.322. And one more. If I do log of negative 4 over log of 2, the log negative 4 over log of 2, I get non-real answers. So since we can't have a negative number on this, we get no solution on that. Just goes as part of our logarithms. One of our things that it says on the outset is that you can't do the log of a negative number. So other great thing is that you'll be working with all positives here unless you get an answer portion that is negative. So that's going over just your first little introduction to logs, how to expand and condense them, and then how to change them so that you can use the calculator to easily get your answer.